1998. Okay, in this case here we get that the pooled variance SP squared is equal to 68,146,146. Okay, I'm just wondering whether I've made a mistake here. Them numbers are very, very big. Okay, let's just see what we have here. Yeah, it does actually say that. It does say that with a standard deviation of 12,000, okay, and a standard deviation of 10,000. So they're just big numbers. So let's not worry too much about it, okay? But it will be counteracted in our test statistic. Okay. So now what we're going to do is we're going to take our test statistic, our t, which is equal to x1 bar. Okay, I said x1 is going to be prime land, so that's PR, minus x2, which is going to be for rockland. Okay, minus mu1, which is going to be the the population mean for prime land, minus mu2, which is the population mean for rockland, and that needs to be divided by the pooled variance, which is SP squared, over N1, which is for prime land, okay, plus SP squared over N2, which is for rockland, if that makes sense, and it's the square root of that. Okay, so let's do this here. Okay, so now we end up with t is equal to the mean of prime land, which is 47,000, so it's 47,000, minus the mean of rockland, which is 44,000, okay, minus the difference under the null hypothesis. Okay, so the difference under the null hypothesis when we have equality. Okay, so under the null hypothesis, under the equality position, we have mu of PR minus mu of R. Well, we have mu of PR equals mu of R under equality, so that means mu of PR minus mu of R is actually equal to, is actually equal to 0. So under the null hypothesis, there's no difference between them. Okay, and so that's going to be 0 here, and that needs to be divided by, okay, well, it's SP squared, which is the variance, the pooled variance, which is 68 million, so that's a big number, 146,146, divided by the sample size, the first sample size, which is 600, okay, plus 68,146,146. Okay, divided by 500, and it's the square root. It's the square root of that. So we have big numbers here. Okay. So what we end up with here, the numerator is, let me just actually maybe fold this over. Okay. So the numerator is going to be 47,000 minus 44,000. Okay. So that gives us a value of 47,000 minus 44,000. So our t is going to be equal to, well, 47,000 minus 44,000 gives us 3,000, okay? And that needs to be divided by the square root of this thing here. Well, let's actually just do that here. This is 146,146 divided by 600, okay? Gives us, it's about 114,000 plus 68,146,146, which needs to be divided by 500. Gives us about 249,869. So we have, it's the square root of 249,869 to the most significant digit here. Yeah, well, not to 0 decimal digits. Okay. So now when we do this here, we get a test statistic of, well, it's 3,000 divided by, let me move that over here. It's 3,000 divided by the square root of 249,869, which gives us a value of, it gives us a test statistic of about 6.00 to 2 decimal places. So it's quite a big test statistic. We're actually 6 standard units, if that makes sense. There's a difference of 6 standard units between the evidence and between the difference in the two samples and what we hypothesize their difference to be, and their difference we're hypothesizing to be 0. Okay, so that's our test statistic. Done. So now what we need to do is we need to calculate our critical values. That's step 4, is our critical values. Okay, our critical values. Okay, so don't forget this is a t distribution, so it's a symmetric distribution. Okay, now for us to show that there's a difference, don't forget the alternative. The alternative was we need to show that PR is bigger than mu r. We want to show if we can prove the alternative, if we can reject H0, well then this is pointing into the right hand tail, okay? But by pointing into the right hand tail, really what we're saying is that mu PR minus mu r is actually bigger than 0. So actually this is a one tail test, okay? So it's a right hand tail test, and what we're going to put in that particular tail here is all of the significance. It's alpha is equal to 0.01 is going to go in there, okay? And don't forget this is centered on 0. So the question we have here is this, is that what is that critical value there? Now to find that particular critical value, we have to go to our t-tables, our t-distribution tables, okay? Our t-distribution tables. Don't forget what we need is our degrees of freedom. Okay? We need to know the area in the right hand tail, which is 0.01, and we also need our degrees of freedom. Our degrees of freedom is equal to n1, the size of the sample for prime land, plus the size of the sample for rockland, minus 2, which is 600, plus 500, minus 2, which is 1100, minus 2, which is equal to 1998. Our degrees of freedom are actually huge here, so we've got huge degrees of freedom, and I don't think our tables is actually going to give us degrees of freedom all the way up to that particular accuracy, but we will be able to get degrees of freedom, I'm sure, up to a couple of hundred from our t-tables. So our t-tables, the t-tables themselves, the amount of area that we're putting in the right hand tail, the amount of area in the right hand tail is listed along here. So we have P is equal to 0.01, and our degrees of freedom are listed down here. Now the tables that we've provided you with, okay, probably don't go up that far. I don't think they do. Okay, actually you can probably see that the best we can actually do for degrees of freedom, okay, is the degrees of freedom is at 200. That's the best that we have here, okay. So coming down to 200. Underneath the column that is P of 0.01. Let me maybe show you that up here a little bit closer. Okay, so 200 degrees of freedom is